of a function.
Thank you, and thank you for inviting me. So what I want to talk about is somehow different from what's being talked about. I want to talk about the section, or a variant of the section conjecture, but I want to talk about it where the field is very large. It's going to be the function field of the moduli space of curves. So, and it seems to me to be a reasonable test case for the section conjecture. So, so I'll take K as a field of characteristic 0. And GK is the Galois group of K bar over K. I'll take MGN, and I'll put, say, over K. M, this is going to be the moduli space. I should really say moduli stack, but it's not going to matter. Say moduli space of genus G curves, smooth genus G curves. Maybe I should say smooth projective genus G curves with n distinct marked points. So that's the G and the N. And the last thing is I want plus a level M structure. So a closed point of this will be essentially the isomorphism class of some genus G curve over a closed field, n points that are all distinct, and they'll be labeled, and also phi, where phi is an isomorphism from H1 of C with Z mod M coefficients into Z mod M to the 2G, and where this respects the intersection pairing. So I'll put the symplectic inner product on this given by this matrix. And so I'll take, I'm going to be taking G to be greater than or equal to 2, N will be greater than or equal to 0, and M will be greater than or equal to 1. And if I take an M here, I have to have the mth roots of unity inside K. So here, for level M, I need the mth roots of unity contained inside K. And I will set K, I'll use K generically for the function field, but sometimes when I want to make it clear where it's coming from, this will be the function field of MGN M. And we also have the universal curve over MGN, or MGN with a level M structure. And so this is the universal curve. And it has n tautological sections. These points here give you sections xj where j equals 1 to n. And what I want to do is restrict the universal curve. By a generic curve of type Gn, I just mean the restriction of the universal curve to this function field. So C will just be the restriction, C over K is the restriction of the universal curve to the generic point of excuse me, MGN with a level M structure. And so this clearly has at least n rational points because these sections here give rational points of the curve, so that you have that x1 up to xn are all, this is contained inside the k rational points of the universal curve. And now it's natural to ask if that's all. So, but before stating a theorem, let me give a slight variant, at least for calculating the rational points. One can do the following. I can consider some smooth closed subvariety of MGN, say M here. I'll call this topologically ample. If pi 1 of x mapping to pi 1 of MGNM, I can make a more general definition than this, but just this will suffice for the moment if this is an isomorphism. And so, so how can you find such x? Well, you can use Zariski-Lefschetz theory, and this is, at least when you take M to be at least 3, this is a quasi-projective variety, and you can take generic linear sections, and as long as that section is generic and the dimension of x is at least 2, then you will have what I'll call it one of these topologically ample subvarieties. In fact, you can make a weaker definition. You don't need this to be an isomorphism. You just need something else to hold, but it's more complicated to describe, so we'll stick with this. So again, here, if you take, you can take the universal curve here and restrict it. So you can look at C over X. So this maps to MGN. And you've got the universal curve here. And you can pull back the universal curve here. You get this curve C over X. And it will also have sections xj. And here I could take k to be the function field of x. And again, you've got that x1 up to xn is contained inside C of k. So, sorry?
If you have a stack, I'm not sure what the function field is about z equals
Okay.
2.
Yeah, so if g equals 2, yeah, it's true. If g equals 2 and m equals 1, there's a problem because every curve is hyperelliptic, so it has an automorphism. But if I take the level to be at least 3, or if I take at least 1 point, then I kill that. And if you're worried about it being a stack, I can, so eventually I'm going to take g to be, I can do most of this with g greater than or equal to 3, but for the talk I'll take g greater than or equal to 4. And in that case, I can take M0, I remove the curves with automorphisms, and they have codimension at least g minus 2. So if you're in genus 4, you're removing something of genus codimension 2, so you don't change the fundamental group. And you get something quite quasi-projective.
Is this C the same as the C over the generic points? And if so, how does it map to X?
Sorry?
This C that you write over there in that diagram.
Oh,
that's
sorry,
not the
this
same
is
as
bad.
right?
Maybe I just use, what I'm going to do is talk about curves over function fields, and I sort of will use C generically for the curve. And I hope in any particular case it's clear what K is and what C is, and if it's not, demand clarification. All right, so the theorem that you would hope is true is that, well, okay, so what's the goal? The goal is to study the section conjecture in this situation. So, and you know, as I understand, the big problem in the subject is actually constructing points out of sections. Here that problem is not going to exist because we're going to try to, I'm going to explain that the expected result is true, that the rational points of such curves are exactly the expected ones. So you know the points in advance, and then you've got to study the sections. All right, so, so the first result is that, so theorem 1 is if C over X is topologically ample, G of type, I should say here, topologically ample of type Gn. The level doesn't really matter. It doesn't really play much of a role. C is topologically ample of type Gn. So I also want, in topologically ample, sorry about this, I want this to be smooth. So topologically ample curves are the base x is smooth.
But it seems that you define this only for curves which lie inside the moduli.
Well, okay. So I could define it to be any variety here that maps to here and induces an isomorphism on pi 1. In fact, I can assume something much weaker. It's just isomorphism on some sort of completion of pi 1. But I just want to give the idea that you can take things other than these, the full moduli space. You can cut the dimension down. And if y over x is an unramified cover, then C of k of y, so the k of y rational points of x is equal to C of the k of x rational points is just equal to x1, xn. So, of course, over the algebraic closure of k of x, you've got lots more rational points. And what this is saying is all the additional rational points are ramified along some non-empty divisor. And, I proved this first, and then Beauville pointed out to me that there's an old theorem here of Hubbard in about, I think it's 72, and Earl, so these are Teichmüller people, Earl and Krah, who generalized it. So this would be the case of n equals 0, and this is the case all n, 76. And they use Banach algebras to prove that if you look at Teichmüller space, so this is Teichmüller space, if you like, this is the topologically the universal cover of the moduli space of curves, and we'll take this to be of type Gn, and there's a universal curve over this. So this guy here is contractible, got no fundamental group. And they proved that the only holomorphic sections of this are the xj's. And in fact, at first I didn't think so, because a rational point is really only gives you a generically defined sections defined away from something of codimension 2. But I've realized since that this theorem implies this result in the case where you take x to be mgn, all of mgn. It doesn't imply it as far as I know when you take x to be an ample subvariety. So this result, so their results imply theorem 1 when x is equal to mgn. So
is the passage from mgn to the sample case difficult?
Sorry?
The passage from the general x is difficult.
Well, the way I proved this originally before I knew about this result was that, and I'll sketch the proof where this covers a level covering of mg. I use structure of the fundamental group, but that proof was very instructive because that's what I use as the tool you develop there, which I'll try to explain, is what you try to understand the group theoretic sections of the standard group extension. So I will sketch a special case of that, which will include these ample subvarieties.
Can I ask a question about this? Are there functions, let's say, on the covering which
suppose we have total covering and just usual curve, concept curve, yeah? Concept curves over the take covering with a disk fiber. Are there functions, global functions, polymorphic functions on this which are non-trivial around the fiber?
Sorry, you're talking about this
Yeah,
situation?
about this,
Sorry?
yeah, about this. Okay, maybe.
I'm not a diagonal person. I mean, I just saw this, and the proof of this is some big thing that involves all sorts of functional analysis.
Okay, okay, no.
All right, but let me make another remark, is that, so I won't, morally, I'll write down what I want to say morally, then I'll write down something correct. So morally, I would like to say it's false in genus 2. And the reason is this. So for example, if you look at M say 2, well, let's just look at M2. So if I don't put an N, it means it's 0. And I take a level 2 structure. Then the universal curve here, so a level 2 structure on it, every curve of genus 2 is hyperelliptic. A level 2 structure is just a labeling of the Weierstrass points. So you get the Weierstrass points are all rational. So you get that W1 through W6 are in C of K of, well, all right, it's K to 0. But if I want to be correct, because as Deline pointed out, there's the function field of this is not well defined, I just have to put some even level like 6 that's greater than 3. And but if this theorem held in genus 2, there should be no points here. And in fact, this theorem of Earl and Kra and all these people say that these are the only sections. So in this case. All right, so now I'm going to, so for the next result, I want to take G to be greater than or equal to 3, and I'm going to take N to be equal to 0. And so again, C is the universal curve over KG0 and some level M here.
For v equals 2, is this correct adverse and taking Weierstrass form?
Sorry?
For v equals 2,
Yes.
do you claim to say that you have just to add the Weierstrass form?
I haven't tried to prove it, and the proof would be very different. And I can explain why later. When you see this proof, you'll see it definitely fails in genus. It fails in general for hyperelliptic curves.
But theorem 1 is you assume v at least 3.
Sorry?
In theorem 1, you assume v at least 3.
Yes. Yeah, sorry. If G is greater than or equal to 3, I didn't. Yeah. So now I take, again, I'm going to take G greater than or equal to 3. And actually, I'm going to take G greater than or equal to 5, sorry. And so, right. Okay, so theorem 2 is that, well, G is greater than or equal to 5, and we're going to suppose that if there exists a prime number L such that the image of the L-adic cyclotomic character from the Galois group of the small field into ZL cross is infinite, then the standard extension 1 into pi 1 of C over K bar into pi 1 of C over K. So K here is KG0 into GK into 1 has no sections. And I'll try to sketch the proof, or give the idea of the proof later on. So here, just in case there's any doubt, k is equal to k g0m, g greater than or equal to 5. So this says that the set, because this curve has no points, the section conjecture is true. So i.e. The section conjecture. M, and I've got to take, say, for example, with k equal to, say, a number field or a finite extension. By the way,
Sorry, that gk is little k. This is big K, sorry.
so yes, this is big K.
But the assumption is on small k, or?
Yeah, well, okay, so what's the point of this assumption? So I want that, so there's a map of gk into GSP of h, where h is the h1 of the curve. And I want this to be Zariski dense. So basically the mapping class group for the pi 1, if you like, pi 1 of mgn surjects onto the integral symplectic group and Zariski dense in the SP part. And so this condition here guarantees that I fill up all of GSP. Right, so that's another way to state the condition, is just that this is Zariski dense. So all right, so if n is positive, I have to consider a variant of the section conjecture, and so not too dissimilar from what Kirsten was talking about yesterday. So so let's now take n greater than or equal to 1, and again, g greater than or equal to 5. So, and I'll take k to be k, g, n, m. We can take any m, it doesn't make any difference. So we have 1 into c pi 1 of c over k bar. So let me call this group, like everybody else, I'll call it pi. And this maps into pi 1 of c over k. And this maps into gk into 1. And now I have various sections. So Sj is equal to xj star. So pick one of the points, say the first one, and then you can write this group here as gk semi-direct product pi. Now if I take any, I can replace pi by anything I can obtain from it functorially. So for example, I could take the pro-L completion, or I could take, what I'm going to do instead though, is to take the unipotent completion over QL, and I'll explain what that is in a second. But I have this extension here, so this will map to here. Strictly speaking, I should map into the QL points of this. GK semi-direct product pi unipotent over QL, and GK here into 1. This will map into here, and I can ask about this guy here, or I can also take this and I can truncate it by terms of its lower central series. So I can take this modulo, say L to the R, where L is the lower central series. So pi unipotent mod L to the R into GK into 1. This is equal. And let me give this. And now I can ask about sections of, for example, here, modulo conjugation, or I can by elements of the kernel, or I can ask about sections here, modulo conjugation by the kernel. So LR is equal to rth term of the lower central series of a group. I just think of it as some functor I applied to a group. And so, just so there's no confusion, L1 of pi equals pi, and L2 of pi equals pi pi, and L3 of pi equals L2 of pi pi. So it's a central series. And so let me just talk a little bit about unipotent completion. So often when I talk about stuff, I talk about completions and everybody's eyes glaze over, but the people here seem to live with completion, so this shouldn't be too bad. So let me I'll just discuss it in the profinite case. So this is, say, profinite. And I can look at, so I can look at all, if I look at the set of all, let me call it phi. Phi takes gamma into, I'll call it U phi QL. So, so this is where U is unipotent, U phi is unipotent over, say, QL, and where phi is continuous. So you look at all, and I'll also ask here that phi is Zariski dense. So I look at all Zariski dense unipotent, continuous unipotent representations. These form an inverse system. So I can take their inverse limit, and the unipotent completion of gamma over QL is just equal to the inverse limit of all the U phis in the system here. And then I have a map from the inverse limit of all of these homomorphisms from this into gamma unipotent over QL, the QL points of this. So this is the unipotent completion, and there's another construction you can define concretely using the group algebra. You can take the group algebra of gamma over QL, you can complete it with respect to the maximal ideal, and you can take the set of group-like elements and you get the same thing. Okay, so yeah. So let me give you one example. If we take pi as above, so pi equals pi 1 c over k bar as above. Another remark is that since in characteristic 0, unipotent groups correspond to nilpotent Lie algebras via the exponential map. So this group here is a pro-unipotent group. It's a pro-unipotent group, and it's completely determined by its Lie algebra, which is a pro-nilpotent Lie algebra. So gamma unipotent over, say, QL corresponds exactly to a pro-nilpotent Lie algebra, which I'll denote by, say, G. It's just the inverse limit of the Lie algebras of all of these guys here. It will just be the inverse limit of the Lie algebras of the U phi. So to describe the unipotent completion of this, I just need to describe the Lie algebra. So I'll let P will be the Lie algebra of pi unipotent. And it's well known that you obtain this by, say, taking a free Lie algebra on generators A1, A2, and so on, B1 up to BG, and you complete it, and you mod out by the ideal generated by the infinitesimal version of the standard relation in pi 1. And it's a good way to think of this as that, so this is really just a basis of h1 of pi. And if you think of this as a representation of the symplectic group, you're just modding out by the intersection form or the, okay. All right, so I want to write star R here. So we have a map from C, M, G, N, so the rational points of this universal curve. And we have a map into the sections of, I don't know if I've still got it. Yeah, so I'll let this be, this extension here be dagger R, and this will be, this guy here will be dagger infinity. So if I take R equal to infinity, I'll take this sequence here. Sections of dagger R modulo conjugation by the kernel, by pi unipotent. And you can ask, is this an isomorphism? So yeah, so here R is an element. I want to look at this for, well, R in, say, 2 infinity. So theorem 3, again, G is greater than or equal to 5. And I guess I'll put M greater than or equal to 1. N is greater than or equal to 1. So I'm using the fact here that the group's a semi-direct product. And whoops. Right, so if K is a finite extension of QP, then star R is a bijection for all R in 3 infinity. Okay. And if K is a number field, then, and I should say here, L is not equal to P, then star R is a bijection for R in 3, 6. And it's definitely not a bijection if I take R equal to 7. And I'll explain later. However, there's an obstruction there that I will explain. However, I believe that it's true with R equals infinity. In fact, after Sidney and Kirsten's talk yesterday, you know, there's an obstruction from going from one stage to the next. And I've never thought about this non-abelian cohomology, but my problem plus her talk prompted me to talk to Mignon and read part of his paper on this non-abelian cohomology. And I think there, if I computed the obstruction correctly, all the obstructions vanish if you have a section that extends all the way out to infinity. It just, I should have said at the beginning, this is work in progress, so I believe there was progress overnight, but it's a little premature to report it as a theorem. Probably a little dangerous. Sorry?
Is L not equal to P necessary here?
Well, maybe with what you know. I mean, things will become clear. It will become clearer why things are working in a minute.
But it's not that you're saying that you just...
No, I just don't know how. I'm a topologist. I'm not a number theorist. So I have to rely on some stuff off the shelf, and I have to rely on what?
Actually, then I have another question.
Sorry?
Okay, since you say you're a topologist, then I have another question.
Have another?
another question.
Ah,
For theorem 2 or theorem 3,
yeah.
if I just formulate very naively over C a topological version, is it false?
No, I think the same proof also works topologically.
With this-
Sorry, these guys here, I would have to replace GQ. I was going to write this up, but it'd be too much of a pain. But I can replace the Galois group. I need a replacement for G little k, and I would have to replace this by pi 1 of, say, the Tanakian category of mixed Hodge structures or something like this, right? I need a theory of weights. And so, you know, I worked this out first with this approach, and then I figured out that it would work over here. And then I need to control extensions, and I should say, why is this 6? It's because there's some extension of Q by Q of 3 that can pop up coming from the ground field.
Right, and I understand, but if I were really silly and
Sorry?
if I were really silly and just looked at the discrete proofs for one of your topologically ample bases, would it be false for some obvious reason?
I have to think about it. I mean, I could try to answer, but I may say something foolish. So, all right. So I want to explain what goes into this because I mean,
Okay, but in the case where there are no terms.
one byproduct of this is maybe it produces a useful tool for looking at the section conjecture in other situations because the techniques seem orthogonal to all the standard ones. And maybe if you combine this with the standard techniques, there might be some.
In this theorem 3, we have some bit vector, but is the set of bounds the only obvious bound?
Yeah. See, this is the theorem 1 told us what the points were. You know, it said there are no unexpected points. And then here, what you have to do is just you have the existing sections. I'll try to sketch the proof or sketch the main points. So I don't know what section I'm up to, but we'll call it 3 basic tools. Not basic fools. All right, so there's 2 basic tools. One is relative, or more accurately, weighted completion. So this is more general than unipotent completion. And I first learned about this in the letter that Deline wrote to me. That was relative completion. And then Matsumoto and I came up with a variant we call weighted completion, which is the appropriate one to use here. And I'll explain relative because it's a little easier. And I'll maybe say something about weighted completion. So this is Deline. And this is and the other thing is there's a density theorem. So the density theorem roughly says that if you take any divisor, this is why I need the genus to be 5, because I need a theorem from topology that is only known in genus 5. But if I take a divisor in mgn, with g greater than or equal to 5, and I look at its normalization, it maps to mg, and I can look at the image of its fundamental group in the symplectic group. And the density theorem says that its fundamental group is Zariski dense. It's a kind of strictness theorem. And for that, I need to know that pic of mg g tensored with q with a level M structure. Here's a place where I need levels is isomorphic to Q, and this was recently proved by Putman. It's long been a conjecture, I think, of Mumford, but it was recently proved by Putman. And A. Putman. So I need this result in this density theorem.
This is only true when g is greater than or equal to 5, this result?
Well, it may be true in genus 4, but his proof is in genus 5, greater than or equal to 5. I mean, I'd be very curious to know if it fails in genus 3. It's definitely false in genus 2, right? But I need to know that every divisor is ample, some multiple, it's ample. And so, I'll take a divisor in mg, I have to do some fooling around, so I have to pass to a cover. It may split into various components, and I need to know that each component's ample. And then I need to apply, Zariski-Lefschetz theory to prove this.
Anything?
Sorry?
MG, what level?
Oh, sorry. Just some level. I won't explain this theorem.
MB1?
It could be 1, yeah, but no, I have a divisor, and the divisor could intersect itself. It could have a double locus. You can get loops that you get around by going around this double locus. It's as if you have a curve like this, and I want to look at the normalization, so I have to get rid of this. And sometimes you can't get rid of it. If you went all the way up to Siegel space and you still get this loop, that's okay. But actually, I don't want to go in this direction. But anyway, all right, so let's talk about relative completion. So the density theorem is what I need to study how this relative completion changes as I move from MG towards a generic point, because you keep removing divisors, and you need to know how cohomology changes. And if you have this density theorem, you can analyze the Giesen sequence, and you see that the cohomology only changes at the trivial representation, which is and since I'm sort of working orthogonal to the trivial representation, this is how I'm, anyway. All right, so let's talk about relative completion. So here's the data. So I'm going to take gamma as profinite. You can also do it with a discrete group. You just forget continuity. And I'll take R as a reductive QL group. So what I'll put here is two examples. So you know what to think of. The first example I'll put here is I'll take gamma to be pi, and here I'll take it to be, if you like, pi 1 of mgn with a level, say over k bar. So this is the same as the profinite completion of the mapping class group, say it's level M subgroup. Okay? So this is something that topologists have studied, and a lot of the leverage I get is because I know a lot about this group. And here I'm going to take the trivial group. So this is the trivial group. And here I take, say, SPH, where H is equal to H1, if you like, of pi. Right? It's just a symplectic group naturally associated to the curve. And then I'm going to have a representation rho, which takes gamma into RQL. So this is continuous and Zariski dense. And if I took pi 1 of mgn over k, here I would take GSP instead of SP, and the condition on the cyclotomic character would be to ensure that this representation is Zariski dense. All right, so here there's nothing to say. I mean, there's just a homomorphism into the trivial group, and here it's, if you like, there's a map from pi 1 of mgn, m, into pi 1 of ag, given by taking a curve to its Jacobian, and this is SP of, say, the integral version of this, and this is the completion of the mapping class group, say level M subgroup, and this homomorphism is very standard. It just this is surjective with m equals 1, and it has finite index if m is positive. So what we're going to, this is like unipotent completion, we're going to, G is going to be the completion. It's going to be the inverse limit over a whole bunch of representations, and I'll tell you exactly which ones, of groups G phi. So what are the G phi? So where you have, and I'll be a bit sloppy and not distinguish between a group and its rational points. So you take a group over QL, so you have, these are all QL groups. And you look at extensions of this, say, by a unipotent group. And you look at homomorphisms into GQ, I'll call it phi. Here's rho here, that lift rho and is Zariski dense. So I want this guy here to be continuous and dense. I look at all of these, you can see they form an inverse system, and the completion here is the sort of the sort of smallest thing that would dominate all of these extensions. And U, its unipotent radical or its pro-unipotent radical will be the inverse limit of the U phis. And so what we get is we get an extension U phi into G, sorry, U into G into R into 1, where this is pro-unipotent. And this is our original reductive group here. So this is reductive. And then under sort of mild hypotheses, there's a version of Levy's theorem which says this splits. So this split's got nothing to do with points. It's just that, so what this says is that G is sort of unnaturally isomorphic to, well, R semi-direct product U. But it's saying that this unipotent group is acted on by this reductive group. So this unipotent group corresponds to a pro-nilpotent Lie algebra. So this is going to be the Lie algebra of big U. And so what you have is, if you want to understand this group, you have to understand the Lie algebra of the unipotent radical as together with the action of the reductive group R. So I should say in this picture over here, what's the completion? So if I put G here will just be pi unipotent if I take the trivial group, right? And if I go over here, I'll call this group here GGN. And I could put a level, but it turns out that this group does not depend upon the level. So the answer here is independent of M. So I'll leave. Okay. So to know G, need to know the Lie algebra U of the unipotent radical plus the action of the reductive group R. So I want to tell you what it is for one particular case. So what's the structure of, and I could give you the whole thing, but it doesn't really matter. I'm going, right. So I have here, I have GGN, UGN, and the Lie algebra of this I'll denote by little UGN. Right, so this will be the Lie algebra of the unipotent radical of this completion of pi 1 of mg. So let's first of all look at UG1. And it's going to, so we're going to have UG1. I should say this has a natural weight filtration which turns out to be its lower central series. Which is its lower central series? Its lower central series. Later on, as we pass to the generic point, you still have a weight filtration, but it will cease to be the lower central series. So I'm going to in fact, all of these do. It's just going to be L R of U G N, right? So what I want to describe, I could describe the whole thing. I mean, I'm essentially doing it, but I'm just UG1, I wanted to take its associated graded with respect to the weight filtration. So in other words, associated graded with respect to the lower central series, and I will mod out by W minus 3. In other words, the third term of the lower central series. So I'm going to describe just this small part here. So this guy here is key in this problem. This is the only invariant I use. So what is it? Well, maybe I'll do this one over here. So it has two graded quotients, -1 and -2. So this is the weight. I get rid of everything in lower weight. So what are the generators? There'll be lambda 3 0 of h plus h. I could also write it as the third exterior power of h, but I want to write it like this. And in degree -2, there's something I'll call Tambo, because it's popular in Japan.
What's h again?
So h, if you like, okay, h is equal to h lower 1 of pi. And the group I'm taking is going to be SPH, or if you like, I call that SPG. Right? And so I'm describing it as representations of this group. And so there'll be a copy of lambda 2 0 of h. And that's all there is. And so what's this guy? This guy's not going to play a role, but I'll tell you what, if lambda 1 through lambda g is a fundamental set of weights for this guy, I'll tell you a different way. It's just the highest weight part of S2 lambda 2 of h, right? This guy Tambo here. But I have to tell you the other two representations, so let me put this up there. So lambda 2 0 of h, it's equal to lambda 2 of h divided by the symplectic form. So if you like, it's the primitive part of h2 of the Jacobian of the curve. And lambda, so theta equals the invariant inner product. It's the intersection form or the cut product, whatever you want to call it. And lambda 3 0 of h, it's the highest weight part of the third exterior power. It's equal to this theta times theta wedge h. So it's the primitive part of h3 of the Jacobian. And now I have to tell you what the brackets are. So what are the brackets? And I should point out, it's more natural, h1 is the abelian part, the weight minus 1 part's more naturally lambda 3 of h, but for the purposes of this, it's better to think of it as this. So let's fix an isomorphism of these guys here. And let me give you the bracket. And the reason I'm going over this is because this is the whole story. It's just because of topology, we understand this thing, and because it behaves well as we go to the generic point, we're able to study sections. So what's the bracket? There's two parts. Well, yeah, there's a part from lambda, and this is for g greater than or equal to 4. In genus 3, it's different. So if I take lambda 3 0 of h tensor 2, it surjects. I'm going to forget about the Tambo part. It plays no role, and I'm going to mod it out in a minute anyway. It surjects onto this lambda 2 0 of h. And then there's a part that's lambda 3 0 of h tensor h, and it also Tambo. This also surjects onto lambda 2 0 of h. So I'm really going to concentrate on this lambda 2 0 of h, and also if you take H tensor H, the bracket here surjects onto lambda 2, 0 of H. And what I want to point out here, and I'm going to write it in red because it's important, is this is degree 0 in H. This has got degree, this is linear in H, and this is quadratic in H, right? So this bracket here does not involve H at all. This one's linear in H, here it is, and this one's quadratic in H because there's two H's. All right, so now let me jazz this up to.
So you are telling in each case there is an obvious map, and that's it.
Yeah. So if you decompose the second exterior power of this, it contains a unique copy of this, and it contains a unique copy of Tambo, and to do this properly, you have to say that how they're all calibrated. I mean, you have to, but you can do that. I should say that UG1 maps into the derivations on P, and so you can completely describe. In fact, and if you take this guy UG1 mod W minus 3, it injects into der P mod W minus 3. And so you just completely describe it by its image in here. In fact, that's how you compute the bracket. So,
Sorry, when you say you calibrate, you mean to make the weights correct or something?
no, but you basically have to, yeah. No, I guess it's okay, the way I said it, yeah. But anyway, let me describe graded weight dot of UGN, and I'll do it mod W minus 3, and in weight minus 1, it's lambda 3, 0 of H plus H to the N. This also includes, this is for N greater than or equal to 0. And in weight minus 2, you get one copy of Tambo. This stuff's coming from just mg, and all the other stuff's coming from adding points. So plus you get lambda 2, 0 of H to the n. So this is like n copies of P modulo W minus 3, right? And then you also get, I'll write it as Q of 1, QL of 1 to the n choose 2, and this is going to correspond to the n choose 2 diagonals between the points. And let me ignore, again, I'm going to ignore everything other. This guy plays a role in some things, but I'm going to ignore this and ignore this. Because you really should focus on this part of it here, which I'm going to later give this a name and call it, maybe I'll do it now, I'll call it DGN. And so what happens here is that the bracket works exactly the same way. There's sort of, if I did it for P, if I take P graded P mod W minus 3, it's got a weight minus 1 part. What's its weight minus 1 part? It's just H. It's just the abelianization. And the commutator sub thing is lambda 2 of H. They're the brackets, but we had to divide out by the symplectic form, so it's lambda 2, 0. And so you're getting n copies of that, one for each of all the points, and the brackets between them all vanish as far as this is concerned. If you bracket two different ones, they go into these guys over here via the polarization. And still, this guy acts diagonally on each of these by this bracket here. And that rigidifies them all. That adds a lot of rigidity, and it also goes, this guy brackets, two guys bracketed in here also go diagonally in here. Okay, so I'm going to call this Lie algebra DGN, and here's the critical lemma. So now I'm taking dgn, which is just the part I've circled. I mod out by this, I mod out by that. And saying if, I'll just put it here, g is greater than or equal to 4, then the only SPH invariant sections of dgn plus 1 to dgn. So here n is greater than or equal to 0. So let me use notation. V will be something in here. And there'll be u0, un. All the u's lie in the copies of h. This map takes this to v, u1, un. There are various sections, namely v, u1, un goes up to v, uj, u1, un. So I'll call this section Sj. These are the only SPH invariant sections, and it's elementary. You can give that. This is easier than Florian's exercise. I could do it, right? It's stupid. It's just, it depends upon this thing. This thing here, to say it's SP invariant says that whatever you put in there, U0 has to be a constant linear combination of the UJs where J is greater than or equal to 1. That's just Schur's lemma. You have to determine the A's. And so the fact that something's, you've got a quadratic, and you have to, Schur's lemma also says on these guys here you have some sort of multiplication. And you play this thing off on the various diagonals, and what you see is that AJ squared's got to be AJ. So AJ is 0 or 1. So every AJ is 0 or 1. And if you do it on the diagonals, you see that AJ, you know, any finite subsum, like AJ plus AR squared has got to be A1 plus AR. So that says any sum of them has got to be 0 or 1. So that says at most one of them can be 1. And then you use the degree 0 part to prove they can't all be 0. And that's it. But this is where I get all the leverage. I guess I'm out of time. In fact, I'm over. So, but let me stop here and say the whole point is, as you go to the generic point, the density theorem tells you that this doesn't change. So this is what allows me to distinguish divisors of degree 0 from points. And the rest of it is just that H1 of GK graded weight, say, minus m of pi unipotent. So if you take little k to be QP, this thing vanishes once m is 2 and beyond. And so once you've gotten started correctly, and that's what this lemma does, it says you can conjugate any section into one of the standard sections. So I'll stop there.
Maybe I ask you a question. So in the variant that you have, where you have the curve over some x, which is contained in mg, or which maps to mg, you said you can lower the dimension up to 2?
Yeah, down to 2, yeah.
So what about dimension 1?
Okay, I have a question, but it's for Professor Deline. Is that, okay, so is there an arithmetic Lefschetz theorem? Suppose you had an arithmetic surface. So you take so I was trying to think about this. I mean, I couldn't see how to do it. But if there's an arithmetic Lefschetz theory, then maybe you can get the dimension down to 1.
Another thing like that.
Okay.
So could you say just 2 words about the algebraic proof of your theorem 1, about that the points are just...
It's easy. It's easy because this relative completion is functorial, right? So if you have, well, the first observation is you've got c over x, and if k is equal to k of x, and you have a rational point ck, that's a rational section of this. But it's defined away from codimension 2. So it's defined on some open where the complement has each component has codimension at least 2. But if this is smooth and you remove stuff of codimension 2, you don't change the fundamental group. In fact, I actually think this extends to everything for some dumb reason. But it doesn't matter. So this tells you that forget about going to the Galois group. You've got a map of pi 1 of C down to pi 1 of X. You get a section. But I basically assume that this is the mapping class group gamma Gn. And this is very close to being gamma Gn plus 1. And now if you look at so you get a section here. It induces a section from GGN, the relative completion up here, to what I call here, it's GGN1. I mean, but now if you look at, and that means you get a section on the unipotent radicals. And if you look at the associated graded, it's going to be SPH invariant. See, I can even take the field to be algebraically closed here. I don't need anything special with K. But then I look at this little part of the unipotent radical, just this little part here, and they're the only sections are these guys. So that's it. You have to worry that you might have a point that differs from one of these standard ones by a point of order m, by some non-zero torsion point. But then that would give you a map from mgn with some level, say, into mg2, where you take it to the possible, the putative point plus the one it differs from by a torsion point. But if you look at the unipotent radicals here, modulo weight minus 3, you can see it just can't happen. I should also say I'm not qualified to do characteristic P without parental supervision. But I believe all these arguments also work in characteristic P. I mean, I've discussed, there was one missing piece, and I had a conversation with Bjorn. He told me something I needed to know, and I think the rest of it's there. So it also works if little k is FP.
Other questions?